Okay, hi. Okay, recordings. Okay, start. Okay, people, thank you for coming. This is the week 5, the last one in November and December. After this, I certainly hope you guys can have a good holiday. I think some of you are already traveling this week, so that's good. I will give you the practices for those who want to practice more. Definitely a good idea during December, but it's not a must. Okay. Now, at 30th and 31st December, which is the Monday and Tuesday before your school starts. Hopefully you guys are back in Singapore and we can do a special 2 days before the school starts. Please try to attend. That will be very useful. But I cannot give you a lot of details right now. It doesn't make a lot of sense if I tell you what's the content. But please come, right? Now, today we're going to use it for, going to divide to half. The second half, I will set your expectation on organic chemistry one more time. So again, to settle things, we are winding it down, so to speak. But in the first half, I noticed there is one new topic that gives people a lot of trouble. And this topic is often taught very weirdly in school. So I'm not sure what is going on with this topic. It's as if all schools teaches it in a way that doesn't help in exam. I really don't know what's going on. That is not true for most topics. So this is especially important for you guys who feel that you guys have a good chemistry class. I'm very glad your chemistry class in school is good. But for some reason, this topic cannot be ignored in exam, but it is taught in a very weird way. Let me just try to present the topic for you in a way that is most suitable for exam. Then hopefully your good class will give you more benefits. For those who feel that they have a bad chemistry class, that means this is again something like your organic chemistry. This is your chance to get a good class, okay? Because you cannot rely on your school, right? So that's what I'm trying to do for this first 1 hour. Now, I will be doing something slightly new. I will be forcing questions out of you. It feels weird because you guys don't even know what the topic is about. Shouldn't you be listening to me? Yes and no. The problem is simple. The problem is simple. For most topics, your teacher, including me, is already so good at the topic, right? We have been studying it for 20 years, whatever, right? We have forgotten what it means to not understand the topic. That's what you're facing right now, right? So I have a lot of good knowledge here, but it will be very bad if I just dump it at you. Very bad, very bad. We need your questions. Okay, we really need your questions from your perspective, a perspective of people who do not understand and trying to start out. Okay, so we will combine our perspectives. Okay, we'll combine a perspective of somebody who knows a lot and you who are fresh out of it. If we don't do that, the result won't be very good. Let's just say that. Okay, now how do we force the question? Some of you are shy. Well, let me try to do it in the best way that I know, right? Okay, now let me share my screen. Nicholas, just to check, you can hear us.
Yes.
Okay, cool. Now, Nicholas, this is not connected to the one just now. Okay, now ostensibly, people, the chapter will be called electrolysis. That's what the chapter will be called, but that's only half the chapter, only half. There is one other thing called battery, and battery or cell, that's the other half. Okay, that's the other half. So two halves of the same principle, right? Now, this one is popular in exam. Popular. This one is a little bit less. However, the problem is for some reason, this is explained first. This is explained first, right? And then they take around 70% of time to explain it. For something which is less popular in exam, and less, I really mean something like the other way around, I suppose, 30%, 70%. I've noticed this happening even in good schools or good classes. I really do not know why. I really do not know why they do it this way, right? Furthermore, this chapter is the one that is more and more important in what you call year 5 or your JC 1. This is it. The electrolysis kind of fades out. But they ostensibly use a lot of time to explain it. Now I'm going to reverse this process. I'm going to discuss this, and electrolysis will follow on later. This is, for now, for the last good news, this is supposed to be the easier one anyway. This is the easier one. So it's easier, it's more impactful exam, and it's more impactful in the future. But they don't spend as much time in battery. I'm going to try to do that. Okay. Now, you don't have to remember all this. That's just me explaining it. Okay. Just know that your teacher will not start with battery lah, for whatever reason. Now, I won't be asking you to ask questions first, lah, right? Not yet. So this is a battery, right? And then what a chemistry student studies, is the inside. The chem student studies inside. You will get a glimpse of what is happening inside the battery. Physics students, some of you are physics students, okay, studies the one outside the battery. So if you're both a physics and a chemistry student, you will understand the outside and the inside. The chemistry student have a very specific interest in what is inside the battery. That's the battery chapter. We are totally ignoring that electrolysis weird guy, totally ignoring it. Okay, again, I'm going to just erase this. So what is inside the battery? Surprisingly, they will not draw it this way. Chem students, you will not see the battery drawn this way at all. No way. You will also not see it drawn this way, so to speak, the inside. Not very useful. Not very useful. These two drawings are not useful in chemistry. They just assume that you know it, but they don't use it a lot. What is a useful drawing in chemistry? You will be surprised. The useful drawing is a container, two metals, most probably, one sort of weird liquid, and connect them, so to speak. Or rather, maybe don't connect them. Maybe I'll just cut it off first. Now, this is the useful drawing in chemistry. This is the useful drawing in chemistry. This is it. This is a useful one. Now, I haven't give you a lot of detail. That is by purpose lah. I'm trying to fish out or trying to get the habit of asking questions from you guys. Okay. Now, so that we don't wait for each other, I'm gonna put your name in the, in order. I'm gonna say, okay, first of all, I think it's Anu. No, I'm gonna area. Then there will be Evan. And then I think that will be Joel. Then there will be Kirana. And then there will be Nick. And then there will be Rachel. 1, 2, 3, 4, 5, 6, 7. Yes, I think that's correct. Okay, so when you ask questions, it's something like this. Okay, oh, I cannot think of any question to ask teacher Philip. Never mind, I just want any question that comes from your mind. Remember, I want you to ask from your blankness, so to speak, your blank slate. I want you to ask from that, right? Therefore, no questions are too shallow or too small. That is what I'm trying to do so that it benefits everybody. Let me repeat this. The question you ask will very likely benefit everybody else. Okay? It will benefit me in a way that I can talk about your point of view more. And as a result, it benefits everybody else. If not, I'll go too fast. Again, there is a reason why I go very slow here. I noticed that this chapter tends to confuse a lot of people. So I have to slow myself down. Unlike OChem, I go fast, people can catch up one. OChem is strange that way. We go fast, no problem, right? But this chapter, we cannot go fast at all. We cannot go fast. Vera, I can see you. Can you hear me?
Yes, I can hear.
Right. So Vera, so happens you're in the last of the name order. Nobody else. Yeah, okay. And I'm trying to start a new chapter, which I believe is very weird. Okay, I've explained to other people why it's weird. And right now, I'm asking everybody's new here, to just start by clarifying my drawing or whatever they want to ask. Okay, I am trying to fish out your point of view, including you, Vera, from a point of view which is, oh, I don't know anything about this chapter. And that's what I'm aiming for. Okay, now let's start with Anu. Anu, ask your question, then Ariel, then Eben. Okay, Anu, ask your question, please.
You know how the wire is not connected. So what's in between the wire?
A very good question, Anu. I hope everybody is hearing that. Look, let's go back to the not useful battery. Turns out that the not useful battery is useful for us. Okay, this is not useful for chem question. Okay, but it's very useful for us. This is the one useful for chem question. Now, you ask yourself, useful for chem question. Or rather, you have to imagine Anu and everybody else that this guy is this battery. In a battery, Anu, your eyes are immediately drawn to what?
The big rectangle.
The big rectangle. Sorry, you mean this thing? This thing?
Yeah.
No, the positive and the negative. I don't know. Maybe that's what you... Look, you're going to use a battery and you're going to replace your remote. You're going to look for the positive and negative polarity. Something like that. Make sense?
Yeah.
Okay. Now, you are saying that these two wires are not connected well. The question is, what is a battery connected in, when we're using a battery, what is it connected to?
Springs.
Fair enough. Here's a spring. That's fair. But the spring is connected to?
A circuit.
And which that circuit is usually a device. Okay? So a battery is connected to a device. Well, that makes a lot of sense, right? A device requires electricity, so we connect it to battery, correct? Therefore, Anu, this is probably a positive or a negative, we don't know. This is probably a positive, negative, we don't know. That's our job. The question won't tell us. And this is connected to a device. Now, have I answered your question, Anu?
Yeah.
Okay. Ariel, next question. Clarify, ask, whatever.
The diagram looks like the electroplating diagram.
Which you have learned electroplating? Really?
Yeah. Like we
What,
saw it in the
Ariel?
lab.
Oh, it's not in the lab.
Yeah.
Hallelujah.
Is it the same principle? Like
Okay.
moving ions.
Okay. At this point, Ariel, I gotta clarify to other people first, yeah? That means you're a little more advanced lah. Let me confirm that nobody has actually done electroplating in lab or even heard about it. Those who have, tell me right now.
I think I've seen it before.
You have done it before, Joy?
I think briefly.
Oh, Anu, you also electroplating, really?
I have heard of it. It came up before in Sec 2, I think.
Very briefly lah, I understand. Okay, now the rest shouldn't, and again, this shouldn't be that fast. Now, even though the setup is very simple, I must admit, the science behind it is the complicated one, the setup. Now, to answer your question, Ariel, now other people listen. Your electroplating is the electrolysis. I did mention electrolysis before. Now, the answer is electrolysis is the opposite of battery. Ariel, this is like, one is differentiation, one is integration. They are obviously connected. They are obviously, therefore, similar, but they are also opposite in some sense. Now, in what sense? Now I'm going to ask Eben. Eben, what do you expect from a battery?
What do I expect?
Correct. What do you think is the job of a battery? Like a normal person. I'm not talking about physics or chemistry. Oh, here's a battery. What do you expect?
Well, it'll provide energy.
Energy in the form of, not light, but in the form of?
Potential.
Yeah, I mean, you're a physics
Yeah.
student, so I guess you can say that. Can I say in a more common people word, you provide electricity lah? Can we say that?
Yeah, okay, yeah.
Now, Eben, of course, as a physics student, I expect you to answer more lah, which is totally fine. So, Eben, a battery provides electricity lah, correct? Now you're also a chemistry student. Providing electricity energy from what energy? You must have learned that energy cannot be destroyed and energy cannot be created. So I am asking you, Eben, the electricity comes from what?
Chemical energy.
Very good.
Yeah.
Some of you will have known this word starting from primary 5 or primary 6 science lah. And we are currently studying the chemical energy conversion into electrical energy conversion. That is the point of the battery chapter. If this doesn't make sense, that will be your question next. Right? Now, back to you, Ariel, a little bit. Your electroplating, Ariel, is the reverse. You are using electrical energy and convert it to chemical energy. Maybe right now it doesn't make a lot of sense, but it is the opposite of battery. Now, does that answer your question?
Yeah.
Okay, good. Now, Joel, ask your question lah.
I understand what's going on right now, so
Okay.
nothing much.
All right. Okay. Then we will, let me just confirm. Kirana, do you have a question?
Like what is the purpose of the setup?
You mean the setup in front of us?
The one you drew.
This thing. Okay. A very good question.
Yeah.
You would wish that a battery is a battery lah, correct or not? You would wish. And
Yeah.
frankly speaking, the drawing in front of us does not look like a battery at all. Let's be fair, correct?
Yeah.
Okay. Now, Kirana, to answer your question, this is a very old battery. When they first kind of designed a battery, it looks like this and it is liquidy. It is liquidy and it is smelly. And it doesn't provide a lot of electricity. But back then, there isn't even any electricity. Now, their point on introducing this because they think this will be easier to understand. Understand or the process of converting chemical energy to electricity is easier if they just use an old drawing, which you will do in lab also because it's also very easy to set up. However, you won't think of it about battery because to you, a battery looks like this. However, after studying it further, I hope you will realize this guy is a battery. Have I answered your question, Kirana?
Yeah.
You have to deal with the unfamiliarity. I am taking something unfamiliar and I'm taking something familiar here and making it unfamiliar for the sake of learning. It feels very weird. That's one of the weirdest thing about this chapter, to be fair. Okay. Now, I will go and further describe the differences between our modern battery and our old battery. We're studying old battery, right? If I don't do that, I notice that you guys will never connect it. You guys will not feel comfortable, in fact. If you guys don't feel comfortable or feel that there's a disconnect, then makes it even harder in exam. Everything we do is for exam, right? Getting comfortable is part of it. Now, I'm just going to describe one or two. Like, for example, the modern battery. I'm going to ask a question back to you, Joel. Is a modern battery wet or not wet? What is your expectation, Joel?
It's dry and solid.
Your expectation is that correct? Very
Yeah.
good. Now, so this guy is dry. How dry? Well, you have had battery leakage before lah. Frankly speaking, it is only kind of dry. Isn't it correct, Joel? If the modern battery leaks, I mean, leaking has a meaning of, oh, it's not that dry actually. Correct or not?
Yeah, it is dry on the outside. And the
Correct.
inside is-
Right. Now, in the inside, good, Joel, is a paste. Paste means a liquid plus another medium. They make the modern battery drier by making the liquid into a paste. That means the liquid is always there. That means you better get used to this liquid. Even though you don't feel like the modern battery has a liquid, it has a paste. That is their effort to making it drier. Okay, Nicholas, any question?
Why is that thing like fully not useful? Like, couldn't like you use that like in a simple diagram? Why is it like fully not useful?
You mean the left one, is it?
Yes.
Because the left one, unfortunately, this guy, which you feel very comfortable with, unfortunately, this guy only show the outer shape, right? And frankly speaking, for normal people, that's what we care about. But it will never show you the inside working. Now, the purpose of the chapter is to discuss the inside working. The purpose of, how did the chemical energy convert to electricity? You can never do that by the left drawing.
So how
Unfortunately.
do you like in primary school you have to draw like these electrical systems, the
Yeah,
simple ones. How would you draw them in secondary school? Like Sec 4?
you mean in a physics, as a physics student lah, because you're not, right? As a physics student. You will draw this one?
Yeah.
This one, no? A physics student will draw this. And please...
No, I'm talking about I mean the right one.
Oh, the right one will never be of interest except for chemistry student, because only a chemistry student investigate the inside of the battery only. A physics student or your sciences in primary 5 and primary 6 generally are only interested in the outside of the battery. That means, what do you use the battery for?
Yeah, but like, how would you draw the system with that one on the right?
Oh, you don't. That means what I told you, chemistry is not interested in the system. That means not the outside of the battery. Something like that. I hope that makes some sense.
Yeah.
No circuit at all here. No electricity. Just the production of electricity. It is a good question, Nicholas. Have I answered it?
Yes.
Okay, Rachel, just to confirm, you have more questions? What is the liquid in the container? Wonderful. Now, please note, Rachel asked that. Now, Rachel has no, mic is not working, and that's what Rachel's typing. Now, notice that the similarity between the old and the new is already, I'm emphasizing, it's both the liquid. Okay, what is the liquid in the thing? It is, well, something that can, electricity can flow. Okay, now this is therefore immediately Sec 3. Immediately Sec 3. You tell me, Rachel, what is the kind of liquid that can allow electricity to flow? From Sec 3. Is it metallic? Now, is it possible that this liquid is a liquid metal? Now, I would agree with you that liquid metal can conduct electricity, and then I'll give this a very big question mark. Must a battery have a liquid metal? I'm going to now ask Vera. Vera, do you have any other possibility of a liquid that can conduct electricity?
Water can conduct electricity, right?
But very badly, right? So improve water, please.
Salt water.
Very good. Salt water. So you say salt water. Now, according to your sec 3, this is now an aqueous ionic. This is what Vera is saying. You should now provide a liquid which is ionic and aqueous, a soluble ionic substance. Why? When an ionic substance is soluble or aqueous, it splits into positive ions and negative ions, and they conduct electricity. Hey, if this appears new, you are totally forgetting your sec 3. This is totally just sec 3. Whether you remember or not, this is a good revision of your sec 3. Okay, for the liquid metal, keep it in mind. It is a very good input from Rachel. We will come to it sooner or later. Right. Now, we are rotating back to Anu. Anu, any questions over?
Not yet.
All right. Now, people, notice how good the questions from yourself and from your other friends are, especially when you're blank. Notice that. Notice how good is it to ask those questions, to receive the answer, blah, blah, blah. Okay, let's do it again. Now, when I detect there isn't much question, I will just, explain a bit more and then, invite more questions. Okay, so the liquid is sec 3 stuff. Well, I was waiting for people to ask another one. Never mind. Ariel, can you ask any more questions? Really? By focusing on this weird drawing, can you ask more questions?
I guess. Like,
Well,
what are the two rectangles?
very good. Was waiting for that. Now, the liquid must conduct electricity, right? I was telling you. Those two rectangles must also conduct electricity. Okay, I hope this makes sense. Now, I will give it back to you, Ariel. Ariel, what do you think those rectangles can be?
Probably some sort of metal.
Metal again, which is our favorite, which is correct, right? The blue ones, okay? Any other option, but not liquid, yeah, metals. Any other option? I'm going to ask Anu. Anu, any other option for conducting electricity, solid? Come on, sec 3 stuff. Sec 3 stuff.
Like compounds in like ionic bonding.
Okay, ionic stuff, right? Ionic substance in solid form never conducts electricity. Why? Because their ion is stuck. They cannot conduct. That is also sec 3. Also sec 3. Anu, I'll get back to you. Eben, you're sec 3. Any other thing that can conduct electricity in a solid state? Uh-oh, you're sec 3. Oh, people.
Besides
Besides metal, besides metal.
like graphite.
Very good. Thank you very much. Graphite. People, thank you for summarizing for us, Eben and Ariel. These are the two most common thing. Most common thing. Because we need some sort of solid, not just some sort of liquid only. We need some sort of solid. And there you go. And I will tell you, in a modern battery, this guy in the middle, if you open a battery, that guy, that's so weird. Okay. That guy is graphite. This guy is graphite. Still being used right now. Still being used. Okay. So a good observation. Now for Ariel, Joel. Oh, it was Ariel, isn't it? Cannot. Okay, I'm going to go further by focusing on the picture again. Now, I invite you guys to draw this. Now I'm inviting you guys to draw this in your good notes. Must get used to this. Okay. I'm going to ask Anu to provide two metals. Two metals, please, Anu. Anu, two metals.
Oh, sorry, I was muted. Iron and copper.
Okay, fine. I'm going to put iron here. I'm going to put copper here. And there are many other metals. So at this point, starting your sec 4 is not sec 3, sec 4, you will be introduced to what you call a metal reactivity series. I'm going to immediately teach you how to memorize. Okay, the way I teach you how to memorize is extremely useful in exam. It's extremely fast, extremely useful, right? So right now, people, I am asking you to draw, and I'm asking you to immediately memorize something totally new. Something totally new, but it's not hard. Okay. Now, first, divide your paper by, by a dotted line, divide that, and then divide it further by 3 by doing this. Carbon, circle, hydrogen, circle, dot, 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 3 dots, dot, 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 3 dots, dot, dot, dot. I'm waiting for thumbs up for you to write all this down. Do me a thumbs up when you're done. Okay, good, Kirana. Okay, good, Ariel. The rest are not done. Okay, Vera. Okay, right. Now, people, I did say metal reactivity series, whatever that is, you don't know yet, that's fine. And I immediately start with carbon and hydrogen, which you will recognize to be not metal. That's super weird, but just follow me for now. Why don't you understand? Because this is totally new. Now, the top one, you will say group metal, metal group 1, metal group 2, metal group 3. For whatever reason, that's what I wrote. That's very simple. The bottom 3 is your noble metals, the metal they use in Olympic medals, right? Copper for bronze later on, silver, and gold. Notice that I want you to immediately write down the chemical symbol. Kirana, you must memorize the chemical symbol, so let's do it. Okay, so 1, 2, 3, copper, silver, gold. Quite easy, right? Easy. The middle one is the most used metal in our daily life, iron, right? Iron. A bit of memorization. On top of Fe is zinc, and on the bottom of Fe is Pb. I'm giving you 10 seconds. I'm going to erase this, whatever this series is, and then I'm going to ask you to do it by yourself. Okay? Please memorize it. You have 5 more seconds. Okay, now I'm erasing it. You also erase your whatever this reactivity series is, and now start to rewrite them. Okay, I'll give you 10 seconds. I'm going to rewrite it myself. Okay, 10 seconds is up. Now, remember how I teach you, okay? Carbon, hydrogen, don't know why. Dot, 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 dot. Group 1, group 2, group 3. Ain't that hard. Copper, silver, gold. Not that hard. Most famous or most used metal, iron in the middle. What is here on top? Let me ask Joel. What is it?
Wait, sorry, I haven't finished copying.
Okay, now you can copy. Right now, anybody else can answer what is on top of Fe?
Zinc.
Zinc, thank you. And what is at the bottom of Fe? Anybody?
Lead.
Very good, which is Pb. We say lead, we write Pb. This is intentional, right? Now, get this in your mind, even though you don't know, especially because you don't know, get it in your mind. It's kind of easy, okay? Easy to do. And this is going to be very useful until exam. Now, I'm going to tell you the first usage of this reactivity series. There are many usage for it, but I'll tell you one. For some reason, Anu has quoted us the metal iron and the metal copper. Looks like we're going to make an iron copper battery. Now, notice that iron is here. And notice that copper is here. The reactivity series tell us the guy on top is more reactive, whatever that means. And the guy at the bottom is less reactive, whatever that means. Look at the bottommost guy. The bottommost guy is gold. Gold, as you know, remains gold. Gold never changes. Gold is forever. Maybe diamond is forever. Gold is also forever. Iron will change.
Sure.
Iron will rust. You're saying, Nicholas?
May I just what is SLI?
I'm sorry, try again. What is what?
SLI.
SLI. Oh, the one on top. Oh,
Yeah.
the one on top is not SLI, it's Sec4. It's Sec4, meaning it's a new thing. Meaning you do not know what this is. I'm teaching you for the first time. Okay, I erased it already. Not important. Okay? Still a good question. Still a good question. Now, iron is higher than copper in the series that you're memorizing. He is asking you to immediately realize, iron is more reactive than copper. Whatever that means, iron has priority to reaction. So what does that mean? Again, what does that mean? Yeah, again, I am basing my conclusion on the memorized reactivity series. Fe, more reactive. Cu, less reactive. Okay? When you have two metals, there's always one which is more reactive and there's one which is less reactive. When this happens, the more reactive one react lah. Okay? The less reactive one don't react lah. Now I'm going to connect them, by the way. If I don't connect the battery, now connecting the battery means something like this. Here's the normal battery. Connecting the battery, tara, then current flows lah, right? Current flows. When I connect this, finally, current will flow. Current will flow. Okay, and the reaction will start. Or more appropriately, because the reaction, current will flow. Okay, we are already starting the discussion of how battery works. Okay, now one more time. Fe, copper. Fe react, copper, no reaction. No reaction. Now, give me two random metal. Who else? Huh? Okay. Kirana, give us two random metals.
Can it be from the reactivity series?
It can be not from the reactivity series. That's okay. I'll teach you how to use it. Maybe it's even better if it is not.
Magnesium and zinc.
Magnesium and zinc. Okay, where do you want to put the magnesium? Left or right?
Left.
Let's put it on the left. Right now, people, let's pretend that this is magnesium and this is zinc. Now, pray tell people after Kira. Nicholas, do you see magnesium in the reactivity series?
No.
It is there.
Huh?
It is there, look again. I challenge Nicholas and Rachel, both of you. Come on, where is magnesium in the
1, 2,
reactivity
3.
series?
Wait. 1, 2, 3.
What does 1, 2, 3 mean? Group 1, group 2, group 3.
Oh,
Nicholas or Rachel, come on, where is magnesium in
Oh.
the reactivity series?
it is in the. I mean, it's in group 2.
Yes.
So
very
it's very
Okay.
reactive.
Very good. Yes, magnesium is very reactive. That's why you use it a lot in lab.
What's C again?
carbon for some strange reason. That's your graphite, by the way. That's your graphite. Okay, carbon and hydrogen is H, and don't know why they are both there. But right now we're just focusing on magnesium and zinc. So magnesium is there in the reactivity series. There you go. And zinc is also there in the reactivity series. Now, the reactivity series helps you to realize who will react and who will not. That's the first most important thing in a battery. So, Rachel, who will react if I have magnesium and zinc? Magnesium will react. Thank you. Why? Because it's higher. Oh, higher. What does higher mean? Oh, the higher one is the more reactive one. React, will not react. Now, I'll mix things up. Okay, I'll mix things up. Vera, I have now zinc and I have now Fe. Vera, help us understand who will react and who will not.
Zinc will react.
And Fe will not. Very good. Thank you. Now, please note, Vera is correct. Why? Referring to the reactivity series, very important. No reaction. And please notice, depending on the combination, look, sometimes zinc will not react. Why? Because it's paired by magnesium. Sometimes zinc will react. Sometimes zinc will react. Why? Because it's being paired with Fe. Of course, it depends on who your pair is. Sometimes Fe will not react. Sometimes Fe will react, depending on your pair. Okay, depending on your pair. See it as a pair. I need you guys to understand this first. Thumbs up, please, or ask a question.
Wait, what happens if both are from the same group?
Which is to say, group 2, right? Okay, there's a magnesium and a calcium. So my reactivity is a very good question, Joel. My reactivity series kind of makes it simpler lah. Calcium and magnesium, they will tell you calcium is on top of magnesium. That should answer your question. Make sense, Joel?
Yeah.
A very good question. Thank you. I have another question. Let me throw it to Vera. Anu, do you think we can use group 1 in batteries?
I don't think so. It'll be too reactive, right?
Yes, it will be too dangerous. In fact, calcium is already rather dangerous. Group 1 more reactive than group 2, and therefore it will make the battery explode. You're converting chemical energy into heat, which is not what you want. Correct. Okay, good. But it's there lah. Group 1 is there for your usage. Now, back to our battery. Okay, back to our battery. Now, this reacting means it's going to be gone, all right? Sooner or later, it's going to be gone. This one will stay. When you're not reacting, it will stay when you're gone. And this is the source of leaking. They will never ask you about leaking in the syllabus nor in the exam. Why am I telling you this? Because I want to connect the old and the new. The new battery still leaks because why? One of the metal will be gone. Why? Because the metal reacts. And by the way, the new battery is just zinc and copper. It's just zinc and copper. Okay. In the case of zinc and copper, Ariel, who will be gone?
Zinc.
And the leaking comes from the fact that the zinc will finally be gone. Okay, old and new, not so different. Okay, one more time, old and new, not so different. Let me ask another question. This container, after Ariel would, Eben, this container, do you think it has any effect on the old battery design or not?
No.
And you are correct. This is just a glass container, not participating air, right?
Yeah.
In the new battery, the container, the outer casing is made out of zinc. This is the casing. And that's why the battery leaks, because the casing itself is the zinc. One more time, don't be too hasty to compare the new and the old. They have some comparison, but in the end, their setup is different. Okay, I'm just trying to bridge them so that it doesn't feel so weird. Okay. After Eben, Joel, any questions or what?
Is the casing only zinc? Or
In
like
the new battery?
in the new battery.
Yeah, because the old one is only a glass container, your beaker, right? In the new one, the casing is zinc and plastic, which is the branding of the battery. Make sense?
Oh, so zinc is the only one.
Zinc
Zinc
is
and
the
plastic.
solid thing behind it, the solid thing
Oh,
behind it.
okay.
Okay, and it will get consumed. Consumed. Good question.
Wait, I have a question.
Yes, Ariel, please.
You know how you said like each side is going to be like positive or negative?
Yeah.
So like the metal
Mhm.
that's on each side will like affect that, right? I don't know
Correct.
that.
Correct.
Oh, okay.
Okay. Ariel's question now borderlines physics, and this is important. In the end, a battery is the cross between chemistry and physics. Chemical to electrical, like it or not, electrical is more physics. Chemistry is more chemical. Here is a device that connects chemistry and physics. That's why you see them in both subjects from a different point of view. Now, Ariel's question is, hey, which metal is positive, which metal is negative? And that is the second step that you must think about. What is the first step? I already tell you. The first step is who reacts. The first step is who reacts. And it is determined by the reactivity series. The second is what is the flow. Now, you have to be able to accept this, okay? Physics, current is a physics thing. Right now, I'm insulting the physics. The physics are silly. Current is wrong. There is no such thing as current. In chemistry, you learn that current is just electron flow in reverse. You learn that there is no such thing as current. There is only electron. That's only correct in the syllabus. That's so difficult to explain. I hate this. You know what? Never mind. In your year 4 syllabus, physics will be interested in current as a representation of electrical energy. Chemistry is not. Chemistry is interested in the electron flow through and through. Your question, Ariel, must be answered with where is the electron flowing? So I'm going to do that. Okay. One more time. If you're not a physics student, you may not be bothered by this. If you're a physics student, you may be, I don't know, but I'm preparing you for it. One more time. When we talk about electrical energy in chemistry, you must think about the electron flow. You get the electron flow wrong, you get it wrong. Okay, and unfortunately, it is quite easy to make sure you're correct, right? So let's use the modern battery, zinc and copper. I'll do it this way first. This one reacts. Now, this one, no. Whenever a metal reacts, you can immediately predict the reaction. Your chemistry needs to be at that level. Let me repeat this one more time. Zinc reacts, you must immediately understand, the reaction is that. Now, the question is, who knows? This one I open. Who knows what the zinc reaction will be in this case? Somebody venture a guess. Okay, I'm going to write down, people. Yeah, I'm going to write down. And I'm saying to you, if your chemistry wants to be good, you better make this something that, oh, yeah, instinctive. Yeah, of course. Of course, that's the reason. Zinc will become zinc plus 2 electrons. This may appear obvious or this may appear totally unfamiliar, but this is the supposed reaction of zinc. I'm inviting questions starting from, I guess, now it's Kirana. Kirana?
Yeah.
Any questions so far?
No.
Okay. If Kirana represents you, you can accept the reaction, then it's going to be very easy. Now, Ariel's question is, where does the electron flow? Okay, that's what the question, Ariel's question means. Now, if you know the reaction, you know that zinc will eject electron and also eject a positive ion. Look, the zinc metal becomes the positive and the negative. I hope that makes sense. The zinc splits into zinc 2 plus, the positive side, and the electron, the negative thing. Now, they only have two way out. There's only two way out. This is the first way, and this is the second way. The first way is into the wire. The second way is into the aqueous the liquid, which is usually water plus. Now, use your chemistry sense or common sense, whichever. The zinc 2 plus, is it easier to go to the wire or is it easier to go to the liquid? One more time. The zinc 2 plus has to go somewhere. It cannot stay. Go to the wire or go to the liquid? Kirana?
Wire.
Zinc 2 plus, go to the wire. Now the wire is solid, right? The wire is solid metal. Can a zinc 2 plus, a metal ion, go into solid metal? Yes or no, Kirana? You can answer, I don't know lah. That's fair. But what do you think?
Wait, but isn't like water like a poor conductor? That's why.
No, water is a poor conductor of electricity. However, in Sec 3, Kirana, they told you this. Water is a very good solvent, an ionic solvent. Do you remember that?
Yeah.
That means water is very good for some reason in accepting positive and negative ions. Okay, so based on our Sec 3 knowledge, I did promise you this is Sec 3, it is possible for the water to accept zinc 2 plus just like that. It is possible. Okay, at least open up to that possibility, because if you don't think it is possible, we will block you. We just discovered a block just now, correct or not, Kirana? Kirana representing everybody. Some of you might be thinking, wait, it doesn't make sense for zinc 2 plus to enter water. It doesn't make sense at all. I tell you, it makes a lot of sense. Water likes ions. The proof is ionic substances dissolve in water. That's the proof. But conceptually, you may resist that. Be careful with that. We have to talk about it. After Kirana. Nicholas, I'll give you another thing. I'll try to convince you another way. Look at the electron. The electron will probably want to enter water or probably want to enter the wire, Nicholas.
Okay.
No. I'm asking you a question. The electron will want to enter the wire or the liquid, which is water.
Wire?
Wire, because electron likes to flow in metal. That one everybody knows. Make sense? Okay, now, therefore, based on Kirana and Nicholas, I will say the reaction, the splitting of zinc to zinc 2 plus and electron will cause it to automatically electron goes to wire, and the zinc 2 plus goes the other way, the liquid, because the water likes positive ion. Plus, this is very good. A positive and negative should not be traveling in the same direction. They will reject each other. So all this makes sense. Positive goes into the water. The electron goes into the metal in the other direction. This is meant to be an instant understanding after you're good at it, which is to say, after 15 minutes of discussing this, you need to say, oh, zinc reacts, electron go in that direction, zinc 2 plus go in. Immediately, that is what in your mind. This is immediate by right. Now,
Teacher,
yes, Nicholas?
when it says H2O plus, is the plus like the charge?
The plus means there's already something else in the liquid. There's some other salt. So maybe I'll just say H2O plus salt, okay? Which is unknown currently. What is that? But it is not just pure water. Am I making any sense?
Mhm.
Okay, that's what it means, but we just haven't discussed about it. Good question. Any other question before I declare a break?
No.
Then, Nicholas, please follow us later using the recording. We'll try to settle this in another 20 minutes. Okay, guys, take a break for 5 minutes. I'll see you later.
Bye.
Bye-bye, Nicholas. Okay, my test, Anu, you are here.
Yes, I'm here.
Okay, Ariel.
Yes.
Okay, Evan.
Yeah.
Okay, Joel.
Yeah.
Okay, Kirana.
Yeah.
Okay, Nicholas is Rachel. Very good. And Vera. Okay, Vera. Okay, good. Now, I am describing to you, I'm describing to reaction. This is the start of chemical energy becoming electrical energy, and where we start to see the electrical energy. We start to see the electron flowing. How do we know the electron goes to the wire? I'm telling you more like this, but the electron don't like to go to water. How do you know the zinc 2 plus goes to water? Zinc 2 plus too big to enter metal. You have never heard a metal ion entering other metal in chemistry? I don't think so lah. But you have heard metal ion entering liquid a lot, especially water. So by right, this is not so unfamiliar to you. One more time, if you do it the other way, if I say zinc 2 plus go here, and electron goes here, I was hoping that you will find that to be extremely weird. That is not how you understand it. If you don't find it weird, then unfortunately, you have to make yourself immune by memorizing. You have to simply memorize the electron goes into the wire. At least that makes some sense. I'm, however, hoping that you have enough sense to think that the other way does not seem to work. That's just my hope. Now, why are we doing this? Because this is essential to the battery, and this is to answer Ariel's question. Ariel's question is basically saying, where is the electricity flow? Okay, because you're interested in the electricity flow in a normal battery. You cannot put the battery wrongly. There must be a correct way of putting the battery. Why? Because the electricity direction matters. Now, please note, physics talks about current, therefore, positive flowing to negative. Chemistry do not talk about current at all. Current doesn't exist to them. Only electron flow exists. So, Rachel, look at this electron flow. You don't have current flow. You have electron flow. Which one is, so to speak, positive, and which one, so to speak, is negative there? Do you have any idea? Any idea? Okay, I'll repeat one more time for Rachel, for everybody else. Look, in a battery, you are interested in the current flow, because if you put it wrongly, the device will not work. To facilitate that, the battery has a positive and negative sign, so to speak. So you just align the positive and negative properly. In our old battery, this weird thing, we have an electron flow, we don't have current. Where is the positive and where is the negative? That is the question, Rachel. You feel free to say you don't know, okay? This is totally new, but if you can make a guess, that would be nice. Is the positive flow from zinc to copper? Oh, Vera, Rachel, are you asking that the zinc 2 plus flows from here to there? That's your question, something like that? Is that your question, Rachel? Rachel, are you okay? Sorry, Rachel. Remember, guys, we're communicating with chat here. Oh, okay. And yes, Rachel, and perhaps everybody else is confused, and that's fine. That's fine. Yeah, that's fine. I'm gonna make it very clear one more time, okay? I'm gonna make it very clear one more time. This is why we go slow. That's why we go slow. Notice that I feel very comfortable erasing stuff because erasing and redrawing is a very good way of making sure whether we understand or not. That. Normal battery looks like. Okay, and this will be your device. The D is the device. First thing first, people, do you understand that the negative and positive is here, and this will be your negative and your positive? I have to point out very clearly because this old battery doesn't look a lot like the new battery. Okay, doesn't look like that. Yeah, those are the thing. Now in the new battery, it's clear that this is positive, it's clear that this is negative, and therefore the current flows like that. Right? Now, this is the inside of the battery, right? Which is not transparent, right? However, in chemistry, we open up the battery and this is the inside of the battery. That is it. That's the inside of the battery. We're very concerned with the inside of the battery. What is the outside, right? The outside is this one. This one is the outside of the battery, where the device is, right? Whatever that is. So therefore, this is the outside of the battery. If somebody is not clear here, if you are confused, you better ask right now. Okay, better clarify it. Okay, I'm withholding my current question. I'm just asking Vera. Vera, anything to clarify?
I'm a little bit confused about like the direction of the electrons.
Which is precisely what we are talking about. Very good. Okay, so now let me repeat for you, Vera and everybody else. Currently, we're talking about zinc and copper, right? And we established that zinc will become zinc 2 plus and electron. Okay, Vera, so far?
Yeah.
Furthermore, we established that the electron will go there and the zinc 2 plus will go into the liquid. So far, so good, Vera?
Yes.
At this point, Vera, the electron flow is established. The electron flow is established. Simply because we notice the zinc is being zinc 2 plus and electron will go into the wire, the zinc 2 plus will go into water. So far, if so good. Now, the electron flow is established. Would that be okay first or not?
Yes.
Anu, is there anything else to clarify?
I wanted to ask, like, since the electron flow,
Yeah.
like, you know how like zinc splits up into zinc 2 plus and like E minus, then does copper do the same? No, since only zinc reacts, right? So is the positive and the negative decided by like which one is more reactive?
Of course, but no, of course that's true. The who is more reactive decides who eject the electron. Meaning, let me draw another battery lah. Let me draw another battery. Okay.
Wait, so
Yes. Go ahead. Go ahead. Ariel.
okay. So like the more reactive one, like so-called ejects the electrons.
For example, look at this one. Like, Ariel, I'll answer your question by showing
Okay.
you another battery, right? Now is zinc on the left, magnesium on the right. And therefore, magnesium more reactive, correct? Correct.
Yeah.
Therefore, magnesium will react, correct? And what does magnesium become? Magnesium will become, tell me, Ariel. Ariel, don't mute. Ariel, don't mute. Yeah.
I'm not sure.
Right. Follow the pattern of zinc. It's very simple. A metal, magnesium, like a zinc, will become a metal ion. Right? In this case, a magnesium will become magnesium how many plus?
2?
It's group 2. Very good. And then don't forget, it will split because there will be another 2 electrons also. It'll split. Make sense?
Yes.
As a result, where will the electron go and where will the Mg2 plus go?
What do you mean, where will it go?
Because when it reacts, it splits. And frankly speaking, a positive and negative cannot stay together. They will drive each other apart.
So it will travel to like
It'll travel,
zinc?
yeah, in that sense. But the
okay.
electron will travel through the
Liquid?
wire. The electron does not enter the liquid. The electron will enter the wire. You have 2 options here. Either, oh yeah, that makes a lot of sense. Electron will of course enter a metal wire, or you memorize low. But you have to get it one way or another. Fair, yeah? Have to. This one have to. This is still essential. So one more time, the electron will travel from the Mg to the zinc direction through the through the
wire,
which is here's the electron, and therefore we establish the Mg2 plus will enter the liquid lah. Okay. Now look at the top battery and look at the bottom battery lah. The electron flow was reversed because of the different situation of the metal. Okay, and that is very important. This is what you do before you figure out the questions later lah. This is the first thing that you do. Okay, metal reactivity and then electron flow. I do need some thumbs up, or I do need some questions and clarification here. Okay. Eben, anything to clarify?
No.
Okay. So the electron flow depends on the situation. That is our job. Okay. The question will ask is, they will ask to remind you, hey, you better figure it out. Most questions don't even remind you to figure it out. They assume you know, yeah, that's the important thing to figure out. Oh, the electron flow is like that. Okay. Now I'll just answer my own question, the most confusing part. The most confusing part is they will ask you to label who is positive and who is negative. Okay. If this confuses you, in the end, you will resort to memorization. That's probably the okay part. Okay, probably okay, right? I'll try my best to explain it. Okay, I'll try my best to explain it. Now, in a physics point of view, the current flows from the positive to a negative outside. Nobody complains. However, from the chemistry point of view, there is no current, there is electron. And electron will flow in the exact opposite way, from the negative to the positive. One more time. Huh? In a normal battery, this is already happening. The current flows like that, from positive to negative, but the electron flows the other way. It is because the current is defined as something positive. The more I explain, the more it confuses some people, because this is a historical baggage. They thought current was positive. Turns out it was a flow of electron. They didn't know until so long, like around 50 years plus, they finally discovered that they thought current is positive. It turns out, oh my goodness, the one flowing is electron and it is negative. At that point, the convention is established and it is too late to change. I am so sorry for this confusion. My point is, based on physics, if you're interested, electron flow flows from negative to positive. If you don't find that to be particularly appealing, then I will just propose that, hey, it makes a lot of sense to say that this guy is the negative and this guy is a positive, because shouldn't an electron flow from the negative side to the positive side? That makes some sense. I certainly hope that's enough for you. Okay, either way, we have to label this. That's what they ask. Okay, now let's try this. Let's try this slowly. Okay, let's try this. Rachel, look at the second battery. Tell me, who is the negative and who is the positive? Is Mg the negative or is zinc the negative? Second battery, yeah? Second battery. If you are not very sure, might as well just take a guess, right? Make a guess, please. Mg is the positive. Now, if I put Mg is positive, according to Rachel, hopefully everybody can see that, hey, wait a minute. If Mg is the positive, that means the electron is emerging from the positive to the negative. Some people may not find this objectionable. Some people might not object, but some people will say, hey, but I thought the electron makes more sense if the electron emerges from the negative into the positive. By right, electron is supposed to go to the more positive side anyway, right? And electron emerges from the more negative side. So instead of saying Mg is positive, why don't, hopefully this makes more sense, why don't we say that the magnesium is the negative side and the zinc is the positive side, and therefore the electron emerges from the negative to the positive. Makes some sense, I hope. Does this work for you, Rachel? Okay. Do either understand or remember that. Vera, just checking. Does that work for you?
Yeah.
Okay. Anu, anything to clarify?
No.
Okay. Now, people, I'll spend 5 more minutes. We will not finish the chapter, of course, but I've covered all the essential things. Now, one more time. The first thing I've covered is who reacts based on reactivity series. Secondly is what is the flow? Very important. You'll see later. Now, the third thing is, I'll try my best. The third thing is, now the reaction is only half complete. This is only half. There is another half, the other half. Okay, the other half, I'm gonna erase this. We are still in the process of understanding the inner working of the battery. We're in the process. Yeah. Now, the electron is flowing here. Here's the Cu. I'm focusing on the Cu. The electron is flowing here. Okay, and the zinc 2 plus is currently entering the water. Currently. Now, I will ask the question. Can Cu accept the electron? Simple question, yeah? Anu, can Cu accept electron? And therefore react with it and become Cu minus. Will that happen?
I don't think so.
Okay, your answer is not I don't know, but definitely no, correct?
Yeah.
Could you please explain to us why? It will be beneficial for everybody.
Is it because it already has a neutral charge, so it doesn't really need to gain any electrons?
It is true that the metal start off neutral, definitely no charge. Now, do notice that some things want to be negative. Do notice that, right? For example, a Cl2, which is neutral, will be quite happy to become Cl minus. And you learn why, Anu, in Sec 3. Why would a Cl want to become Cl minus? Your Sec 3 people, Anu and everybody, okay. It is to complete the outer balance. Remember, Cl is group 7, correct? Group 7. And when he accepts an electron, he becomes full and he is happy. A Sec 3 stuff. Very important behavior. Now, Anu proposes that this is not going to happen, and I totally agree with her. I was hoping that everybody will remember the reason. The reason is because this guy is non-metal and this guy is metal. Have you heard of a metal wanting to accept electron to, get his outer shell full? Have you ever heard about that? Okay. If what I'm saying doesn't make sense at all, that means you do forget your Sec 3 and this becomes a very good revision. This is part of the reason why the chapter is confusing if your foundation is not solid. If your foundation is solid, I am emphasizing metal will never accept electron. Metal will never accept electron and therefore Cu will never become Cu minus. No metal will be willing to do that. No metal. A non-metal will totally be willing to do that, a non-metal. Okay, but currently we have Cu. So the electron will continue its journey, no problem. Nothing will happen to Cu. This is the reason why Cu does not react. Cu does not react. One more time, Cu does not react because Cu cannot react with the electron to become Cu minus. Just to be clear, Cu plus zinc 2 plus, nothing much will happen also. So nothing will happen to you. This is the reason why. Of all the available raw material, there is nothing that can affect Cu. Cu will stay Cu. Okay, so we still have these two things left. Wow, will they actually meet? Zinc 2 plus meets electron and become zinc plus again? Is that what will happen in a battery? Surprisingly, no, this will never happen, right? Okay, something else will happen. Also not this, also not that, not all these things. So what will happen is the guy inside the liquid, finally the liquid has some role to play, right? So now let's say the liquid is NaCl aqueous. Why? Because it can just be a simple salt water. Guys, a battery is just zinc, Cu, and salt water. That will work. Okay, so in an aqueous thing, you have Na plus, you have Cl minus, and you have other things. Is this too much for today? Yeah, perhaps this is too much for today. I'll try my best. Now, guys, we have to look for what happens to the electron and the zinc 2 plus. We have to look for it. Okay, that's our job when we want to understand the battery. They do make the big deal out of this, I suppose, right? So my job consists of finding who will accept the electron. Okay, and I've identified many other candidates because Cu is not the candidate. Zinc 2 plus, I will tell you later why also not the candidate. The candidate lies in the liquid. Sodium plus, Cl minus, H plus, and OH minus. Both this comes from the water. This comes from the salt inside the water. Okay, now who is likely to accept the electron? Okay, the answer is this guy. H plus electron will become oxygen. I put 2 here, I put 2 here. And this is your gas. Right? I will try my best to make this as familiar as possible. Okay, who has their battery, bloated? Somebody please have their modern battery bloated. Anybody? Come on, nobody have a battery bank bloated before? Really? Nobody? No way, man. Joel, have you had your battery bank or your phone battery bloated before?
No.
No?
But I've seen it on YouTube. But no.
Really? Really? Anybody else? Rachel, Vera, Kirana, you have not experienced a bloated battery before?
No.
No. No? Really?
Wait, bloated as in like spoiled.
When it's bloated, it's not necessarily spoiled, but it's bloated. The battery actually expands like a balloon.
No,
Have you ever had that before, Kirana?
no.
Really? Okay, so maybe in the older battery, oh wow. Okay, then how am I supposed to make it familiar? Okay, so I have my share of bloated batteries, and this is the proof. A battery produces gas, and that's why it can be bloated. Modern batteries have a good way of absorbing the gas or something like that. Now, in the older batteries, if you don't absorb it properly, there you go. This is what happened. The H plus meets the electron, they become hydrogen gas. The hydrogen gas is very well sealed in the battery gets bloated. Okay, the battery gets bloated. And this reaction, and this flow. So there are three things, right? The first reaction, the second reaction, and the flow. They are most interested in this as a basic question for the battery. This is how the battery changes from chemical energy to electrical energy. Oh dear. Might as well just show. There you go. Right? Here is a simple paper 2 question. Okay. If what I explained to you is correct, okay, is essential, so to speak, you should be able to understand this question, and you should, oh my goodness, this question is too, and this question, oh, this question is too predictable. Okay. Okay, I didn't prepare that question, okay? But when I see it, it's, oh my goodness, it's so predictable, right? So remember, science, math, science. Whenever you study science, whatever the question is, there is always a very standard way of answering, because science is always about something that repeats. Whatever you're studying, it always happens in nature. Nature repeats itself. You're studying natural law. You're studying a law not made by human being, but it is embedded in the world itself. That law simply means certain things keep on happening. Now you go back to science exam. If science exam actually studies about science, if chemistry actually studies about what happens in real life, in its natural world, then the same thing will happen. No matter what the question is asking, the answer will be that thing. Now I've tried to communicate to you what is that thing, as best as I can in 1.5 hours. Now you will see for yourself whether that thing is enough to make you understand the question, right? Even though it's totally new. If it does, then at least you have the confidence that what I'm teaching you is the essence. Whatever the question is, this is what you hold. This is what you give the question. This is what the question maker will test, this thing. That's science. It's not humanities. Okay? Oh. Okay, totally new to you, right, people? So now, I'm going to ask you to identify the familiar things, or at least things that you remember. Okay, at least that. Okay, I'm not going to show you what I'm doing just now. I'm just going to rely on what is in your mind. If you cannot remember anything, who blames you, man? Who blames you? But if you remember something, that's a big bonus. Now, let's start from Anu. Anu and everybody else, please identify one thing which, oh, that's the familiar thing. Oh, that's what we're talking about just now. Go ahead, Anu.
The A part 1.
A part 1 is the flow of electron.
Yeah.
We keep talking about it, and the question immediately asks, hey, I fulfill my promise, something like that. Okay, good, Anu. Let's continue to Ariel. Ariel, did you see anything familiar here? It may be the drawing, it may be the question, it may be anything you want.
Yeah, the drawing.
The drawing. So in what way? Just tell me lah. Just tell. In what way?
Like the copper and zinc, and then
The copper and zinc is there. What else?
the wire.
The wire is there. Here you go. Okay. You may also
Yeah.
point out something unfamiliar lah, but is there anything else familiar?
The liquid and the container. Yeah.
Okay, the liquid and container. So everything is correct there. Now, if you guys run out, thank you very much, Ariel. If you guys run out of familiar stuff, then you find out what is unfamiliar, which is also a fair thing to point out, right? Okay, Eben, familiar or unfamiliar lah?
Uh, which one? Sorry.
Okay, through all this question, which you almost have no idea 1.5 hours ago, point out the elements that you feel, oh yeah, I was talking about that, familiar stuff lah. Oh, this thing we never talk about, that's unfamiliar. Would you please point out whether certain things are familiar or certain things are unfamiliar?
We've seen this like setup. Like, yeah.
I'm sorry,
Yeah.
Evan, try again.
Maybe not the same elements, but like these two batteries. We've seen it.
These two batteries, sorry, what do you mean by the two batteries?
Is it?
Is this two battery? Your question is this two batteries? Am I correct?
Yeah.
Okay. Now, very important thing from Eben. Okay. Guys, this is not two batteries. Okay. This is only one battery. Okay. This is actually a battery. The inside of a battery has two metals. Although it is not obvious from the outside, it's not obvious from the usual battery that we see. This is not one battery. This is not one battery. This ain't one battery. This is not another battery. This whole thing is one battery. I want to clarify that misunderstanding from the start. That thing is just a metal. A battery consists of two metals and one liquid, simply put. Does that at least, can you accept that, Eben? That is a battery. Two metals, one liquid.
Yeah.
Okay, and therefore, this is not two batteries, this is just one. Would that be okay?
Yeah.
Okay, good. And I'm glad we can clarify that. Okay, now, Joel, whatever is familiar or whatever is unfamiliar or a question, that would be great.
Wait, why is there a voltmeter in a battery?
I was waiting for that question. Very good. Okay, yeah. The voltmeter in question is this. So a voltmeter was never discussed just now, and a voltmeter now appears. Now, strangely speaking, this always appears. So a bit weird lah. A bit weird that I never introduced this until, to answer your question, Joel, until if I put a voltmeter here in physics, Joel, you are a physics student, correct?
Yeah.
If I put a voltmeter like this, now, is it the same as this position, just to confirm? Same thing?
Yes.
Now, does it make sense for me to put a voltmeter like this in physics?
No. Like, which diagram are you referring to?
Let's try this thing first.
Yeah, it makes sense.
That makes sense. Now, for those who are not a physics student, it's very understandable if you are even more confused, right? Even the physics student are a little bit confused. How come there's a voltmeter? Now oh my goodness, I don't have my voltmeter here. Oh, I hate this very much. I don't have a voltmeter here. Okay. Never mind. I'm going to show you something. Joel's question is, how come there's a voltmeter? And I'm telling you, oh, they always do that, but why, right? Now here's a big battery, it's a small battery. I'm using a big battery just for clarity purposes, right? Looks easier. A battery has a positive and a battery has a negative here, right? It's a big battery. Now, putting the voltmeter, this is my hand's the voltmeter. This is what the question was doing just now. The voltmeter is connected to the battery. Let me tell you why this makes a lot of sense, okay? Because when a voltmeter, the word itself already tells you a meter for a volt, a device to measure the voltage of the battery. I know if you don't take physics, you don't worry about voltage, but just take it that a battery has a voltage. And you know that a battery's voltage is usually 1.5 here. If you have a real voltmeter, you will discover that it's usually for a new battery around 1.6. That's the expectation. Now, a voltmeter attached to a battery is the same thing as, oh, I'm inviting you, voltmeter. The battery is saying, I'm inviting you, voltmeter, to measure my volt, which is something healthy to do. A battery which runs out will measure around 1.1 volt. Okay, to your surprise, maybe next time I will show you. I don't have a voltmeter. Right now, one more time, a battery voltmeter. The battery is inviting the voltmeter to measure the volt by actually flowing a bit of current there. That's why you have a voltmeter, right? That's why you have a voltmeter. Now, that is not very different from this. Okay. Now, here's a very normal device in your house which requires battery. And here's the battery. Okay, the battery has to be done in a proper way. Now, we just take one out. This is the battery without the device. Okay, now when I put the battery in, I am inviting the device to take the electricity from the battery, right? No different from if I have a battery and I put a voltmeter in. I'm inviting the voltmeter to take some current in order to measure the voltage. So one more time, whether the thing gripping the battery is a device, which is normal for physics. In physics, you will see a lot of devices. Or in chemistry, for some strange reason, they choose the voltmeter. It is the same thing. It is inviting whatever is outside there to take some electricity from the battery, to have a flow of current, to have a flow of electron, in the case of voltmeter, so that you can measure the battery. In the case of the remote, so that the remote can function. Think about the voltmeter as another device which, so to speak, requires the battery. If you can accept that, not very weird, then hopefully that helps you understand. Now, at this point, any questions so far? Okay, let me try again. Let me try to do the question again. Okay. If the voltmeter disturbs you, let me give you the good news. They never ask you to use the voltmeter. Okay, this question appears to do that, but that's not the point. I'll explain later, right? Now, if the voltmeter bothers you and it is always there, then I suggest you just replace it with, in your mind, just replace it with a device. Okay, which kind of makes a lot of sense because a device requires a battery. Okay, if that settles the issue, then good for you. Okay, that should remove some of the problems, right? So, Joel, does that kind of answer your question?
Yeah.
Okay. Kirana, either identify something which is familiar or ask about something else.
Why got the dilute sulfuric acid?
A very good question, right? Now, the liquid must be there, right? And the liquid must be conducting, right? Now, if the liquid is not conducting, how can, so to speak, current flow? you must have a closed circuit. Is that okay first, Kirana?
Yeah.
Because the liquid must conduct. If the liquid cannot conduct, the circuit is cut off and no flow is possible. So the liquid must conduct. Again, it's okay, Kirana?
Yeah.
The question is dilute sulfuric acid conductive? Do you know or not? It's a Sec 3 question actually.
Yeah.
And why is dilute sulfuric acid conductive?
I just know it can react with metal. I forgot the reason.
The reaction is fine, but the reaction is not the aim. My question is, can it conduct electricity? Now, let me revise for you, Kirana, and for everybody else. The sulfuric acid is aqueous, and it is H2SO4. The moment something is aqueous, it will split into its positive and negative ions. You learn in Sec 3, this is the reason why, well, sulfuric acid is conductive because it is aqueous. It has positive and negative ions to facilitate the conduction. Okay, Kirana, am I saying something that sounds familiar?
Yeah.
Okay, hopefully, and that should motivate you to learn the Sec 3 one more. Okay, now I agree sulfuric acid is new, but hopefully now it is not very confusing. Okay, more questions, please, Rachel, and then Vera. Either questions or identify something familiar.
Wait, can I clarify?
Yes.
Is it both the H plus and the SO4 2 minus ions will conduct?
According to Sec 3, okay, yes, in Sec 3, they say the mobile ions in the aqueous stuff. The mobile ion means the mobile positive ion and the mobile negative ion because it is true they are all flying around freely in the liquid, if that makes some sense.
Okay.
Does that make it more confusing to imagine the current? Yes, but chemistry kind of don't care about it. They just want you to say the words, yeah, they're conducting and both conducts, something like that, Vera. Would that be acceptable?
Yes.
Okay, a good question. Rachel, anything to clarify or anything to say, yeah, I noticed this guy is familiar? Rachel, you okay? Just checking. Rachel, okay. Okay, all right. Now, let me just go on to the questions and hopefully convince you that what we studied is like, oh, yeah, see, they keep asking this. Oh, maybe teacher Philip is correct. Maybe this is essential, right? So the flow of electron. Now, back to Anu. Anu, is the first step the flow of electron? I teach you just now. Is that the first step? That's first, second, and third. Or let me put it another way. What is the first thing I teach you to think about immediately? Let me jog your memory. This thing. What is this?
The reactivity.
And
Which
why
one is
do
more
we
reactive?
refer to reactivity? Because you want to know who is
More
more
reactive.
And who is more reactive? Zinc is
Zinc.
here, copper
Yeah.
is here, right? And zinc
Zinc.
are more reactive. So people, the first step is who is more reactive? And because of that, Anu, again, let's just complete it. This is the first step. If it is more reactive, it reacts, correct?
Yeah.
Okay. And the reaction will be?
Zn
Becoming?
2 plus 2 electrons.
And the second step. What is the second step, Ariel? Okay. Believe it or not, that was what you were I was asking you just now. So do you remember the second step, Ariel?
The flow of like electrons
Yeah. So who goes where? So electron go where?
through the wire to like the other side.
And the zinc 2 plus will enter the liquid, correct?
Yeah.
Now, Ariel, do the honor. Have we answered A part 1?
Yeah.
Correct. That's it, look. Guys, we have answered A part 1. I have proven to you that that guy is important, even if it just feels for the mark. I'm telling you, it's important for the whole understanding. Later on, you have to use this. The question is always like that, right? They ask you a question which seems simple, but it's actually very important later on. So done. Okay. Now, write a ionic half equation, whatever this is, for the reaction taking place at the negative electrode. I promise you the labeling was important. If you do not know where the negative electrode is, you can't even do it, right? You can't even do it. So, Eben, how do I propose we label the negative and positive just now? Remember, yeah, you're a physics student, the current is not here, correct? The current cannot help you. We look at the electron itself, okay? The electron will emerge from positive or negative?
Negative.
Negative. And the electron will travel to positive or negative?
Positive.
Because negative is attracted to positive, at least you guys and everybody at least learn that. Make sense, Eben?
Yeah.
Now, based on that, do you know what negative electrode means? Who is it, Eben? The negative electrode is this one. This one is the positive electrode. That's why the labeling is important. They will not tell you who is positive and negative. They will just use it. Eben and everybody else. Do you understand?
Yeah.
Then Eben, do us the honor. This ionic half equation, whatever that is, he's asking you for a reaction taking place at the negative electrode. Have we done that, or do we still have to do something else? Give us your opinion. Okay, let's consider this a new question. Joel, what do you think? Joel, what do you think? Do we still have to do something else, or do we already have the answer?
Don't we already have the answer?
What is the answer? Help us.
Like zinc 2 plus 2 E minus.
You are absolutely correct for completing this, however, solid and aqueous.
Oh.
For those who understand, good for you. We already have the answer. And hopefully I fulfill to you my promise. I was discussing all the essential stuff. See, they asked that. If somebody don't understand, and that is the reaction taking place at the negative electrode, is the zinc converting to this and that. If you don't understand, please clarify right now. I'm inviting you to clarify, yeah? Kirana, okay?
Yeah.
Rachel and Vera, okay? Oh, Rachel, I see you. Okay, good. Now, again, my promise is not just, oh, this will happen in exam, but these two things will help you with the remaining question. Now, the remaining question will be new. Okay, the remaining question will be new. Hey, not so new also, right? The experiment is repeated with zinc electrode replaced by iron. Okay, now do us a favor, Kirana. Did we talk about this, or is this totally new? Did we actually do something like that just now or not?
Like change the metal.
Changing the metal and whatever, right? The question is saying, oh, let's change the metal. Did we do that?
Yeah.
Yes, we did. So by right, this is not new, correct? Okay. Now, what we do is we just draw back, right? Oh, you want to change the zinc, don't forget the position of the zinc is on the right. So now this is Fe, right? However, discussing the change will be new lah. Discussing the change will be new. Now, I want to ask Rachel. Rachel, where is Fe in the reactivity series? if you are here, at least chat with me. Please tell me that you are back. Hey, we probably shouldn't wait. Yeah. Anu, please tell us where is Fe in the reactivity series.
It's below zinc.
Very good. Fe here. Now, people, this discussion will feel just slightly new and so easy to understand. I promise you. Yeah, stay with me. This is battery number 2, right? This is battery number 1, the original battery. The battery number 1 has a slightly bigger distance than battery number 2. Okay, you use your gut. You use your gut to guess which one is the stronger battery. Anu, just use your gut.
The one with iron.
The one with iron, the one with smaller distance will be the bigger or the, so to speak, the stronger battery. That's your gut, correct, Anu?
Yeah.
Okay, again, it's a gut thingy, like we do not know. So let's ask another person. Maybe another person has a different perspective. Ariel, what do you think? Which battery will be stronger or better or whatever lah? Battery number 1 or battery number 2?
Wait, which one's number 1 and which one's number 2 again?
Number 1 is the original one in the question, zinc and copper, correct? He said,
Yeah.
okay. He go and change the metal for us. He go and change, the zinc with iron. He's the one changing it. Now we have 2 batteries. Battery number 1, zinc and copper. Battery number 2, iron and copper. So far, so good, Ariel?
Yeah.
Now, gut feeling. Who is the stronger battery?
Iron and copper and zinc and copper, right?
Yeah, correct. Which battery will be stronger?
Zinc and copper.
Right. So one option here and one option here. And Rachel, yes, I noticed, right? If you miss a little bit of the discussion, we are here and just check the recording. So if we have 1 vote for battery number 2 and 1 vote for battery number 1. I'll continue the vote. Okay, everybody will vote. Evan, what does your gut say? Who is stronger?
Copper.
It's both zinc copper and Fe copper, right? Both.
Oh yeah, sorry, just Fe copper.
Your vote goes to Fe copper, am I correct?
Yeah.
Okay. 2 votes for Fe copper, that's the stronger battery. Okay. 1 vote for zinc copper. This is our gut feeling. Joel, last vote, please.
I vote zinc copper.
All right, we have a tie vote. Everybody else should have a gut feeling. Now I'll tell you the science lah with the explanation. Hey, the zinc copper one will be stronger. Simply because you're using, so to speak, a more reactive metal compared to a slightly less reactive metal, according to the reactivity series, right? Okay, because zinc is more reactive, he wants to react more, he will push out the electron more, you will get a stronger battery. Which is to say, if I now change it to Mg and copper, it will be even stronger. I hope you see how the reactivity series is very useful in many things. This is now serving you a function you never thought before. Okay? It can predict the strength of the battery. Yes, it can. Okay, the comparison between metal is the more gap it is, the more reactive the differences, the stronger the battery. I hope it does make some sense. Even though your gut is wrong, hey, it's just a gut feeling. Now you know the answer. Okay, now, Joel, can I invite you to put into words what this one? Have some courage. This is totally new to you. Let's close today by you. Please help.
The change in voltmeter reading increases.
The first battery is stronger, correct?
The
second battery is slightly weaker. The voltmeter reading will be decreasing
decrease slightly.
Good, good. The voltmeter will decrease slightly. That is the stating. Explanation?
As Fe is less reactive than Cu.
in your mind according to the reactive series. And that is all the explanation needed. Do you understand, Joel?
Yeah.
Everybody else, can you follow until the last 2 marks? Have a thumbs up or clarify. Good, Vera. Good, Ariel. Good, Anu. Good, Rachel. Right. Okay. Now, let's just stop. See, the last one, I'll just tell you, the last one is going to be the easiest one. That's in QA. They like to put QA here. Your teacher will take care of it. That part, your teachers are very good at explaining. I'm very concerned with all the other parts. Okay. Before we close, thank you very much for observing this new topic. Okay, this is a new topic and I fulfilled my minimum promise. I'm trying to convince you what we are talking about today is essential. The proof is in the exam. Later, as we show more exam questions, hopefully you'll get better and better. Oh, correct. Yeah, this is important. Okay. But that will happen in Sec 4. Okay. Good job for today. There isn't much notes right now. I'm just trying to influence your mind. Okay. The note itself will be quite simple. I will give you during Sec 4. Okay. Hopefully there's nothing else, and I will see you guys for AMAth. Okay. Vera and Rachel, if I could persuade you to attend, then again, no, never mind. No, I think everything, no, cannot. Okay, anyway, I'll see you guys tomorrow, those who attend AMAth. All right?
Thank you.
Okay, thank you.
Thank you.
All right.
Thank you.
Okay, welcome.
Oh, tomorrow? Is it
Yes,
tomorrow?
Evan, tomorrow AMAth.
Is it not Wednesday?
Oh, Wednesday. What am I talking about? Wednesday. Sorry, Evan.